Projective Geometry, Volume 1, by Oswald Veblen and John Wesley Young. Chapter 1, Theorems of Alignment and the Principle of Duality. Section 12, the Theorems of Alignment for a space of n dimensions. We have already called attention to the fact that assumptions E3', whereby we limit ourselves to the consideration of a space of only 3 dimensions, is entirely arbitrary. This section is devoted to the discussion of the theorems of alignment, i.e. theorems derivable from assumptions A and E0, for a space of any number of dimensions. In this section, then, we make use of assumptions A and E0 only. Definition: if P0, P1, P2, Pn are n plus 1 points not on the same n-1 space, and Sn-1 is an n-1 space on P1, P2, Pn, the class Sn of all points on the lines joining P0 to the points of Sn-1 is called the n-space determined by P0 and Sn-1. As a 3 space has already been defined, this definition clearly determines the meaning of n-space for every positive integral value of n. We shall use Sn as a symbol for an n-space, calling a plane a 2-space, and a line a 1-space, and a point a 0-space when this is convenient. S0 is then a symbol for a point. Definition: an SR is on an ST, and an ST is on an SR, where R is less than T, provided that every point of SR is a point of ST. Definition: K points are said to be independent if there is no Sk-2 which contains them all. Corresponding to the theorems of sections 6 through 9, we shall now establish the propositions contained in the following theorems, Sn1, Sn2, and Sn3. As these propositions have all been proved for the case n equal to 3, it is sufficient to prove them on the hypothesis that they have already been proved for the cases n equals 3 for n-1, i.e. we assume that the propositions contained in theorem Sn-1, a, b, c, d, e, f have been proved and derive theorems Sn1, a, b through f from them. By the principle of mathematical induction, this establishes the theorem for any n. Theorem Sn1. Let the n-space Sn be defined by the point R0 and the n-1 space Rn-1. A. There is an n-space on any n plus 1 independent points. B. Any line on 2 points of Sn has 1 point in common with Rn-1 and is on Sn. C. Any SR with R less than n on R plus 1 independent points of Sn is on Sn. D. Any SR, R less than n, on R plus 1 independent points of Sn has an SR-1 in common with Rn-1, provided the R plus 1 point are not all on Rn-1. E. Any line L on 2 points of Sn has 1 point in common with any Sn-1 on Sn. F. If T0 and Tn-1, where T0 is not on Tn-1, are any point and any n-1 space respectively on the n-space determined by R0 and Rn-1, the latter n-space is the same as that determined by T0 and Tn-1. Proof A. Let the n plus 1 independent points be P0, P1, Pn. Then the points P1, P2, Pn are independent. For otherwise, there would exist an Sn-2 containing them all by definition, and this Sn-2 with P0 would determine an Sn-1 containing all the points P0, P1, Pn, contrary to the hypothesis that they are independent. Hence, by theorem Sn-1, 1, point A, there is an Sn-1 on the points P1, P2, Pn, and this Sn-1 with P0 determines an n-space, which is on the points P0, P1, P2, Pn. B. If the line L is on R0 or Rn-1, the proposition is evident from the definition of Sn. If L is not on R0 or Rn-1, let A and B be the given points of L which are on Sn. The lines R0A and R0B then meet Rn-1 in 2 points A' and B' respectively. The line L then meets the 2 lines B' R0 and R0A', and hence by assumption A3 it must meet the line A' B' in a point P, which is on Rn-1 by theorem Sn-1, one point B. To show that every point of L is on Sn, consider the points A, A' and P. Any line joining an arbitrary point Q of L to R0 meets the 2 lines PA and AA', and hence by assumption A3 meets the 3rd line A'P. But every point of A'P is on Rn-1 by theorem Sn-1, one point B, and hence Q is by definition a point of Sn. C. This may be proved by induction with respect to R. For R equals 1, it reduces to theorem Sn1 point B. If the proposition is true for R equal to k minus 1, all the points of an Sk on k plus 1 independent points of Sn are, by definition and theorem Sk1 point F, on lines joining one of these points to the points of the Sk minus 1 determined by the remaining k points. But under the hypothesis of the induction, this Sk minus 1 is on Sn, and hence by theorem Sn1 point B, all points of Sk are on Sn. D. Let R plus 1 independent points of Sn be P0, P1, Pr, and let P0 be not on Rn-1. Each of the lines P0, Pk, for k equals 1 through R, has a point Qk in common with Rn-1 by Sn1 point B. The points Q1, Q2, Qr are independent, for if not, they would all be on the same Sr-2, which together with P0 would determine an Sr-1 containing all the points Pk by Sr-1, one point B. Hence, by Sr-1, one point A, there is an Sr-1 on Q1, Q2, Qr, which by C is on both Sr and Sn. E. We will suppose first that one of the given points is R0. Let the other be A. By definition, L then meets Rn-1 in a point A', and by Sn-1, one point B, in only one such point. If R0 is on Sn-1, no proof is required for this case. Suppose, then, that R0 is not on Sn-1, and let C be any point of Sn-1. The line R0C meets Rn-1 in a point C' by definition. By D, Sn-1 has in common with Rn-1 and n-2 space Rn-2. And by theorem Sn-1, one point E, this has in common with the line A'C' at least one point D'. All points of the line D'C are then on Sn-1 by Sn-1, one point B. Now the line L meets the 2 lines C'D' and Cc', and hence it meets the line Cd' by assumption A3, and has at least one point on Sn-1. We will now suppose, secondly, that both of the given points are distinct from R0. Let them be denoted by A and B, and suppose that R0 is not on Sn-1. By the case just considered, the lines R0A and R0B meet Sn-1 in 2 points A' and B' respectively. The line L, which meets R0 A' and R0 B' must then meet A' B' in a point which, by theorem Sn-1, one point B, is on Sn-1. Suppose finally that R0 is on Sn-1, still under the hypothesis that L is not on R0. By D, Sn-1 meets Rn-1 in an n-2 space Qn-2, and the plane R0L meets Rn-1 in a line L'. By theorem Sn-1, one point E, L' and Qn-2 have in common at least one point P. Now the lines L and R0P are on the plane R0L and hence have in common a point Q by theorem S2, one point E, which is equal to theorem 5. By Sn-1, one point B, the point Q is common to Sn-1 and L. F. Let the n space determined by T0 and Tn-1 be denoted by Tn. Any point of Tn is on a line joining T0 with some point of Tn-1. Hence, by B, every point on Tn is on Sn. Let P be any point of Sn distinct from T0. The line T0P meets Tn-1 in a point by E. Hence, every point of Sn is a point of Tn. Corollary: on n plus 1 independent points, there is one and but one Sn. This is a consequence of theorems Sn 1.a and Sn 1.f. The formal proof is left as an exercise. Theorem Sn2. An Sr and an Sk having in common an Sp but not an Sp plus 1 are on a common Sr plus k minus p and are not both on the same Sn if n is less than r plus k minus p. Proof: if k is equal to p, Sk is on Sr. If k is greater than p, let P1 be a point on Sk, not on Sp. Then P1 and Sr determine an Sr plus 1, and P1 and Sp and Sp plus 1, such that Sp plus 1 is contained in Sr plus 1 and Sk. If k is greater than p plus 1, let P2 be a point of Sk not on Sp plus 1. Then P2 and Sr plus 1 determines an Sr plus 2, while P2 and Sp plus 1 determine an Sp plus 2, which is on Sr plus 2 and Sk. This process can be continued until there results an Sp plus I containing all the points of Sk. By theorem Sn1 corollary, we have I equal to k minus p. At this stage in the process, we obtain an Sr plus k minus p, which contains both Sr and Sk. The argument just made shows that P1, P2, P, k minus p, together with any set Q1, Q2, Q, r plus 1 of r plus 1 independent points of Sr, constitutes a set of r plus k minus p plus 1 independent points, each of which is either in Sr or Sk. If Sr and Sk were both on an Sn, where n is less than r plus k minus p, these could not be independent. Theorem Sn3. An Sr and an Sk contained in an Sn are both on the same Sr plus k minus n. Proof: if there were less than r plus k minus n plus 1 independent points common to Sr and Sk, say r plus k minus n points, they would, by theorem Sn2, determine an Sq, where q is equal to r plus k minus the quantity r plus k minus n minus 1, equal to n plus 1. Theorems Sn2 and Sn3 can be remembered and applied very easily by means of a diagram in which Sn is represented by n plus 1 points. Thus, if n equals 3, we have a set of 4 points. That any two S2s have an S1 in common corresponds to the fact that any two sets of 3 must have at least 2 points in common. In the general case, a set of r plus 1 points and a set of k plus 1 selected from the same set of n plus 1 have in common at least r plus k minus n plus 1 points, and this corresponds to the last theorem. This diagram is what our assumption would describe directly if assumption E0 were replaced by the assumption every line contains 2 and only 2 points. If one wishes to confine one's attention to the geometry of a space of a given number of dimensions, assumptions E2, E3, and E3' may be replaced by the following. Assumption En. Not all points are on the same Sk if k is less than n. Assumption En'. If S is an Sn, all points are on S. For every Sn, there is a principle of duality analogous to that which we have discussed for n equal to 3. In Sn, the duality is between Sk and Sn minus k minus 1, counting a point as S0, for all k's from 0 to n minus 1. If n is odd, there is a self-dual space in Sn. If n is even, Sn contains no self-dual space. Exercises. 1. State and prove the theorems of duality in S5 in Sn. 2. If m plus 1 is the number of points on a line, how many Sk's are there in Sn? 3. State the assumptions of the extension by which to replace assumptions En and En' for spaces of an infinite number of dimensions. Make use of the transfinite numbers. Projective Geometry, Volume 1. This book was written by Oswald Veblen and John Wesley Young. It was published by Blaisdell Publishing Company, London, 1910, and is now in the public domain. It is read by Jim Renholt, with programming and illustration by Jim Renholt, 2019. Thank you for listening.